Einstein, Geometry in the Real World. New Modern Translation 2025. Albert Einstein and Harry Yoon, Ph.D. Translator. Foreword by the translator Harry Yoon, Ph.D. This booklet contains the lecture given by Einstein, titled Geometry and Experience, before the Prussian Academy of Sciences in January 1921. Its transcript was subsequently published in February 1921 as a separate book in Germany. Its copyright expired in the United States, and most likely in most other countries, and this booklet includes a new English translation of the original lecture note presented in German. The question of the relationship between mathematics and physics is an ongoing debate since the time of Pythagoras. Many people believe that mathematics is at the foundation of our universe, a la Plato. Eugene Wigner, for example, coined the phrase, the unusual effectiveness of mathematics in physics, which is more or less interpreted again as the fact that the universe is built on some mathematical principles. Interestingly, Einstein was not one of them. Despite the fact that his general theory of relativity is based on a purely mathematical theory, namely, the differential geometry of Gauss and Riemann, he himself never believed that mathematics was anything more than simply a language. In Einstein's view, pure mathematics has no significance in physics. Mathematics is relevant to the description of nature only to the extent that is experimentally observable or verifiable. He uses the term practical geometry, for example, to refer to a certain subset of geometry which has pertinence to physics. In particular, in this lecture note, which spans roughly 20 pages, Einstein describes certain aspects of practical geometry pretty much as a branch of physics, which are related to relativity. Before we move on Einstein's lecture, a quick remark is in order about the translation of the German word Lagerungsgesetz. Its literal translation in English may be storage laws or the laws of storage. Einstein, in fact, uses this word Lagerungs in many of his writings, as related to geometry. This word can be understood, besides storage, as arrangement, placement, disposition, or positioning, and so forth. Gesetz means laws. Now, there is no direct translation for this phrase in English, such as the laws of storage, or arrangement, or placement, etc. But the concept exists, and it is in fact closely related to packing, as in packing balls in a box. The problem of optimal packing dates as far back as the time of Archimedes. The problems of covering and tiling are also related. The interested reader can look up these topics before reading the main content. But all these terms, as used in geometry and combinatorics, have connotations of optimization. Hence, translating Lagerungsgesetz into laws of packing, for example, can be somewhat misleading. Long story short, we ended up choosing to use the phrase laws of relative positioning, which is not a commonly used term in geometry or even in general. We encourage the reader to carefully evaluate the meaning of this phrase on their own, in the context of and based on the totality of Einstein's lecture. Note, this new translation is organized into a number of small sections which did not exist in the originally published German book. The headings are all added by the translator. In this regards, the content should be considered strongly editorialized. Geometry and Experience by Albert Einstein. Mathematics and Other Sciences. There is a reason why mathematics enjoys an eminent status above all other sciences. The propositions of mathematics are exact and precise, and they are indisputable. In contrast, those of all other sciences are always open to debate to some extent, and they are in a constant danger of potentially being contradicted or falsified by newly discovered facts. Nevertheless, if the propositions of mathematics are only related to the objects of the human imagination, and not to those of the real world, the researchers in different fields need not be too envious of the mathematicians. It would be hardly interesting to simply draw straightforward and logically inevitable conclusions from the basic propositions, axioms that we agreed on in the first place, merely using the formal methods to derive other propositions from these axioms. Mathematics would not produce anything truly new if that were the case. But in reality, it is mathematics that in fact gives the exact natural sciences some measure of certainty which they could not have attained otherwise. The great prestige of mathematics indeed comes from this fact. Mathematics and the objects of the real world. Then a truly baffling question arises, which has deeply troubled philosophers throughout history. How is it possible that mathematics, which is after all an invention of human thought, and which is independent of all experience, describes the objects of reality so well and with such preciseness? Is human reason indeed capable of comprehending the nature of the real world by mere thought process, without experience? In my opinion, the answer to this question can be concisely expressed as follows. Insofar as the propositions of mathematics relate to reality, they are not absolute. And insofar as they are absolute, they do not relate to reality. It seems to me that people started realizing the crux of the matter with full clarity only through the recent trend in mathematics, which is known as axiomatics. The progress made by axiomatic mathematics primarily consists in the fact that it has systematically separated the logical formalism from the factual or experiential elements. According to the general tenets of axiomatics, it is only the logical formalism that comprises the subject of study in mathematics. And the logical formalism does not deal with the sensory or other intuitive or experiential elements of the real world. Axiomatics. Let us now consider axioms of geometry from this point of view. Here's an example. Given any 2 points in space, there always exists one and only one straight line which passes through these 2 points. How should this particular axiom be interpreted differently, namely, in the older sense on the one hand and in the more modern sense on the other? The older interpretation. Everyone has certain knowledge, and everyone knows what a straight line is and what a point is, for instance. As to whether this knowledge originates from the faculty of the human mind, or from experience, from some combination of the two, or from some other source, the mathematician does not have to know or care. They leave the question to the philosopher. Based on this knowledge, which comes before all mathematics, the above axiom, as well as all other axioms, is self-evident, that is, it is simply a straightforward result of this a priori knowledge. The newer interpretation. Geometry deals with objects that are formally denoted by the words such as straight line, point, etc. No a priori knowledge or intuition is presupposed about these objects. Instead, it is only assumed that the axioms such as the one above are valid, which are likewise to be taken in a purely formal manner. The axioms are free creations of the human mind. All other theorems in geometry are logical deductions from these axioms, which can only be understood formally, but not intuitively or experientially. It is the axioms that define the objects which geometry deals with in the first place. It was therefore rather appropriate that Schlick called the axioms implicit definitions in his book on epistemology. This view of axioms, which is advocated by modern axiomatics, rids mathematics of all elements that are not inherent in mathematics. It thus eliminates the mystical obscurity which previously plagued the foundations of mathematics. But such a restricted and purified representation also makes it evident that mathematics, defined in such a way, is capable of describing neither the objects of our intuition nor the objects of reality. In axiomatic geometry, the words like point, straight line, etc., are just empty conceptual entities devoid of any meanings. What gives them meaning is not part of mathematics. On the other hand, however, it is certain that mathematics in general, and geometry in particular, originally owes its existence to the need to learn about the behavior of real-world objects. The origin of the word geometry, which means earth measurement in ancient Greek, clearly supports this point. The measurement of the Earth deals with the possibilities of the relative positioning of certain natural bodies with respect to each other, namely, parts of the Earth's body, measuring cords, measuring sticks, and so forth. It is clear that, within the conceptual framework of axiomatic geometry alone, we cannot make any definite statements about the behavior of such real-world objects, which we will refer to as practically rigid bodies. In order to be able to make statements about real-world objects, therefore, geometry must be stripped of its purely logical and formal character by connecting tangible objects of reality, experiences, to the empty conceptual entities of axiomatic geometry. We can accomplish this by simply adding the following proposition to axiomatic geometry. Solid bodies of the real world behave like geometric objects of Euclidean geometry of 3 dimensions, in terms of their relative positioning possibilities. Then, the theorems of Euclidean geometry can be viewed as statements about the behavior of practically rigid bodies. Practical geometry. Geometry extended in this way is clearly a natural science. We can almost say that it is the oldest branch of physics. Their statements are ultimately based on induction from experience, and not just on deduction through pure logic. We will call this extended geometry practical geometry in the following, in contrast with pure geometry, or purely axiomatic geometry. The question as to whether the practical geometry of the universe is Euclidean or not has a well-defined meaning, and its answer can only be provided by experience. All length measurement in physics belongs to practical geometry in this sense, including geodesic and astronomical measurement of length, if we take into account the empirical principle that light propagates in a straight line, and indeed in a straight line in the meaning of practical geometry. I attach special importance to this conception of geometry because without it, it would have been impossible for me to develop the theory of relativity. Without this conceptual framework, the following formulation would not have been possible. In a reference frame rotating relative to an inertial reference frame, the relative positioning laws of practically rigid bodies do not correspond to those of Euclidean geometry due to the Lorentz contraction. Therefore, if we are to treat both inertial and non-inertial frames on an equal footing, then we need to give up Euclidean geometry. Certainly, we could not have taken the decisive step of transitioning to generally covariant equations if the above interpretation had not been available as its theoretical basis. If we discard the correspondence between the objects of axiomatic Euclidean geometry and the practically rigid bodies of reality, which was once considered sacred, then we immediately arrive at the following view, which was particularly valued by the astute and profound thinker Henri Poincaré. From all of the conceivable axiomatic geometries, Euclidean geometry is distinguished by its simplicity. Now, since axiomatic geometry alone does not contain any assertions about the reality that can be experienced, and it can only do so in combination with physical laws, it should be possible, and even preferable, to still stick to Euclidean geometry, whatever reality may be. If contradictions between theory and experience are ever found, then one would rather be inclined to change the physical laws than to change the axiomatic Euclidean geometry. However, if one ends up abandoning the relationship between the practically rigid body and geometry, then one will in fact not easily free oneself from the orthodox view that Euclidean geometry should be taken as special because it is the simplest. Practically rigid bodies. Why did Poincaré and other researchers reject so easily the evident correspondence between the practically rigid bodies of experience and the objects of geometry? It was simply because, upon close inspection, the solid bodies of nature are not truly rigid. Their geometric behaviors, e.g., their relative positioning possibilities, depend on physical conditions such as temperature, external forces, etc. Thus, the original direct and immediate relationship between geometry and physical reality appears to have fallen apart, and now one seems to be inevitably led to the following more general view, which essentially amounts to Poincaré's point of view. Geometry G says nothing about the behavior of things in real world, but rather only the geometry, together with the laws of physics, P, in its totality. Using symbols, we can say that only the sum of G plus B is subject to the control of experience. Hence, G can be chosen arbitrarily, as can also be parts of P. All these laws are mere conventions. In order to avoid contradictions, it is only necessary to choose the remainder of P in such a way that G and the entire P together conform to the experiences. When viewed in this way, axiomatic geometry and the part of the laws of nature that have been relegated to conventions appear to be epistemologically equivalent. Subspecie aeternitatis, Poincaré is right in this regards, in my opinion. The concept of the rigid measuring stick, along with the concept of the clock which measures time in coordination with the measuring stick in the theory of relativity, does not find an exactly corresponding object in the real world. It is also clear that the rigid body and the clock should not play the role of fundamental building blocks in the conceptual framework of physics that cannot be further reduced. But rather, they should play the role of composite structures, which are not supposed to play an independent role in the foundations of theoretical physics. However, it is my conviction that, at the present stage of development of theoretical physics, these concepts will still have to be regarded as independent basic building blocks because we are still far from having such complete knowledge of the theoretical foundations that would provide exact theoretical constructions for these structures. Furthermore, as to the objection that there are no really rigid bodies in nature, and that therefore the properties attributed to such bodies do not apply to physical reality at all, this objection is by no means as ominous and dooming as it might appear at first from a cursory examination. At the end of the day, because it is not too difficult to determine the physical state of a measuring stick as precisely as possible, its behavior with regard to the relative positioning to other measuring sticks is sufficiently well defined. And hence, a measuring stick can be substituted for the rigid body. Statements about rigid bodies should be related to such measuring sticks in practical geometry. The principle of practical geometry. All practical geometries rely on an assumption or a principle that is accessible to experience. We will now try and visually introduce this principle through mental pictures. Suppose that there are marked 2 points on a practically rigid body. We can connect 2 such marked points with a straight line segment. The line segment between 2 points is what we call a line interval in space, or simply a line interval. Now let us imagine 2 such practically rigid bodies, each with a line interval marked on it. These 2 line intervals are said to be equal to each other if the marked interval on one body can be brought through a continuous rigid movement to coincide with the marked interval on the other body. Based on this definition, we assume the following as a hypothesis. If 2 line intervals are found to be equal to each other once and somewhere, then they are always equal to each other and anywhere. The ideal clock theorem. Not only practical Euclidean geometry is based on this assumption, but also are its subsequent generalization, practical Riemannian geometry, and hence the general theory of relativity. Out of the many empirical evidences which speak in favor of the validity of this assumption, I will mention only one here. The phenomenon of propagation of light in vacuum assigns a time interval of a local clock to a line interval in space, that is, the associated light path traveled in that time interval and vice versa. This is because of the fact that the above assumption for line intervals must also apply to clock time intervals in the theory of relativity. It can then be formulated as a theorem as follows. If 2 ideal clocks, placed immediately next to each other, are found to be running at the same rate at any one time and at any one place, then they always run at the same rate, regardless of when and where they are compared with each other. If this theorem were not valid for natural clocks, the natural spectral frequencies of the individual atoms of the same chemical element would not agree with each other as precisely as experience shows. The existence of sharp spectral lines provides a convincing empirical proof for the aforementioned principle of practical geometry. Ultimately, it is based on this principle that we can meaningfully speak of a metric in the sense of Riemann's 4-dimensional space-time continuum. Space-time geometry. The question of whether this space-time continuum is structured according to the general Riemannian scheme or in some other way is, according to the view advocated here, an inherently physical question that must be answered by experience. And it is not a question of mere convention, which is to be chosen on the basis of expediency. Riemannian geometry will be found to be valid if the laws of relative positioning of practically rigid bodies approach those of Euclidean geometry more closely as the dimensions of the spacetime region under consideration become smaller. Geometry at a subatomic level. The physical interpretation of geometry presented here becomes invalid when it is applied, as is, to spaces of the subatomic scale. However, it still retains part of its significance with respect to the questions of the constitution of elementary particles. We can say this because, although the physical field concept was originally created to describe the geometric behavior of bodies larger than an atom, we can always try to give physical significance to this field concept, even when we are attempting to describe the elementary particles with electrical charges that constitute matter. Only a successful outcome, in the final analysis, can determine whether such an attempt is justified, which ascribes any physical reality to the basic concepts of Riemannian geometry beyond the scope of their originally established physical definitions. It may as well turn out that this extrapolation is no more appropriate than an attempt to apply the statistical concept of temperature to parts of a body at the atomic scale. Geometry at cosmic scales. It appears less problematic to try to extend the concepts of practical geometry to spaces of cosmic proportions. One might still object on the grounds that the greater the spatial extension of a construction that is composed of rigid rods, the further it departs from the ideal rigidity. But it is difficult to ascribe any real significance, which is based on any known fundamental principles, to this objection. For this reason, it seems to me that it is a perfectly reasonable question, in the context of practical geometry, to ask whether the universe is spatially finite or not. I do not think it is entirely impossible to imagine that this question will be answered by astronomers in the foreseeable future. The universe according to general relativity. Let us consider what the general theory of relativity teaches us in this regard. According to this theory, there are two possibilities. The first possibility: the universe is spatially infinite. This is possible only if the average spatial density of matter concentrated in the stars vanishes in space, that is, if the ratio of the total mass of all stars to the size of the space over which they are scattered asymptotically approaches the value of zero, as the spaces under consideration are allowed to become indefinitely larger and larger. Then, the second possibility: the universe is spatially finite. This must be the case if there is a non-zero average density of ponderable matter in space. The size of the universe is determined by the average density of matter. The smaller the average density, the greater the size. Hypothesis of a finite universe. I will have to mention at this point that a theoretical argument can be made in favor of the hypothesis of the universe being finite, that is, the second possibility. According to the general theory of relativity, the more ponderable masses there are in the vicinity of a particular body, the greater its inertia. It therefore seems altogether obvious that the whole inertial effect of a body of mass should be traced back to its interaction with the other bodies in the universe, just as gravity, since Newton, has been completely traced back to the interaction between bodies. It can be deduced from the field equations of the general theory of relativity that this complete reduction of inertia to mutual interaction between masses, a la Ernst Mach, is only possible if the universe is spatially finite. Many physicists and astronomers do not seem to be persuaded by this argument. Ultimately, however, it is only experience that can decide which of these two possibilities is realized in nature. What kind of observations or experiments can provide an answer to this question? At first, it may appear possible that the average density of matter could be determined by observing the part of the universe that is currently accessible to our observation. But this naive expectation is misleading. The distribution of visible stars in the universe is extremely irregular. Therefore, we should not carelessly conclude, without any further observational evidence, that the average density of the stellar matter in the universe is equal to the average density in the Milky Way galaxy. In general, no matter how large the space being explored may be, one could never conclude that there should be no more stars outside of this space. An estimation of the average density, therefore, appears to be pretty much out of the question, even approximately. But there is another way, which seems to me more feasible in practice. This approach also presents great difficulties, though. If we consider the deviations of the consequences of the general theory of relativity, compared to those of Newton's theory, which are accessible to astronomical observations, then first of all, we find a deviation which becomes more apparent in a close proximity of the gravitational mass. This particular prediction has been confirmed in the case of the planet Mercury. In the event that the universe is spatially finite, however, there would be another deviation from Newton's theory, which can be expressed in the language of Newton's theory as follows. Gravitational field is of such a nature as if it were generated not only by the ponderable masses, but in addition by a mass density of negative sign, which is uniformly distributed over space. Since this fictitious mass density would have to be extremely small, it could only be noticeable in gravitational systems of a very large extent. Suppose, for example, that we know the statistical distribution of the stars in the Milky Way and their masses. Then we can calculate, according to Newton's law, the gravitational field as well as the average velocities which these stars must have, so that the Milky Way may not collapse in on itself due to the mutual gravitational pulls of its stars, but rather maintain its spatial extent. Now, if the real velocities of the stars, which can be measured, would turn out to be smaller than the calculated values, then it would be a proof that the actual gravitational attractions at large distances are smaller than those according to Newton's law. From such a deviation, one could indirectly confirm the finiteness of the universe, and one could even estimate its spatial size. Can we imagine a three-dimensional universe in our mind, which is finite in size and yet still unbounded? A finite but unbounded universe. The usual answer to this question would appear to be no, but that is not correct. The purpose of the following remarks is to demonstrate, using an example, that the correct answer should be to the contrary. In particular, I want to show you that we can, without too much difficulty, form a clear mental picture of the theory of the finiteness of the universe, in which we can feel easily at home, with a little bit of practice. First, let me make a quick comment of the epistemological nature. A theory of geometry of nature as such is necessarily incomprehensible at first, since it is merely a system of abstract concepts. But these concepts serve ultimately to bring into a coherent mental picture a multitude of real or imagined sensory experiences. To get a mental picture of a geometrical theory means then to acquire an abundance of those sensory experiences whose schematic connection is provided by the theory. In our case, we have to ask ourselves the following question. How can we conceive the behavior of practically rigid bodies, in terms of their relative positioning with respect to each other, through touches, but without overlaps, which is consistent with the theory of the finiteness of the universe? Everything that I am going to say in this regard is not completely new. But the countless inquiries made to me prove to me that the intellectual needs of the people curious about this matter have not yet been fully satisfied. I hope the people who are already familiar with the subject, please forgive me if I bring up some of the things that have long been known. To begin with, what do we mean if we say that our space is infinite? Nothing more than the fact that we could put an arbitrarily large number of bodies of the same size next to each other without ever making space full. Let us imagine that we have a large number of cube-shaped boxes, all with the same size. We can place them on top of each other, next to each other, and one behind the other, etc., according to Euclidean geometry, in such a way that an arbitrarily large part of space is filled. But this construction process could never be finished. We could always place new cubes on the outside without ever running out of space. This is what we mean to express when we say that space is infinite. It would be more accurate to say, as a matter of fact, that space is infinite with respect to practically rigid bodies, provided that the laws of relative positioning for these rigid bodies are given by Euclidean geometry. Another example of an infinite continuum is the plane. On a planar surface, we can place square-shaped cardboard tiles of the same size next to each other in such a way that each of the four sides of a cardboard square rests on one side of another square that is adjacent to it. Again, the construction is never finished. New cardboard squares can always be added, as long as their relative positioning laws correspond to those of the flat shapes in Euclidean geometry. The plane is therefore infinite with respect to the two-dimensional cardboard squares. Accordingly, we say that the plane is an infinite continuum of two dimensions. Likewise, we say that space is an infinite continuum of three dimensions. I can probably assume that everyone knows what is meant here by the number of dimensions. A 2D finite and unbounded space. Now let us consider an example of a two-dimensional continuum which is finite in size but nonetheless unbounded, that is, having no outer limits or bounds. We imagine the surface of a large globe of a spherical shape. Suppose that we have a lot of disc-shaped small pieces of paper, all of which are identical. We place one of the discs somewhere on the surface of the globe. If we arbitrarily move it around on the surface of the globe with our finger, we will not come across any limit or bound anywhere on this journey. We therefore say that the spherical surface of the globe is an unlimited or unbounded continuum. The spherical surface is also a finite size continuum. If you stick these paper discs onto the globe in such a way that no two discs are ever overlapped with each other, then the globe surface will eventually become so full that no discs can be added anymore. This means that the spherical surface of the globe is finite in relation to these circular paper discs. The spherical surface is also a non-Euclidean continuum of two dimensions. That is to say, the relative positioning laws for the rigid shapes lying on this surface do not correspond to those of the two-dimensional Euclidean plane. Figure: circular discs. This can be illustrated as follows. Arrange 6 circular discs in a circle around a circular disc, and 6 around each of these discs, and so on. If this construction is made on the planar surface, it will create a full covering of the surface without any overlaps, in which every disc not lying on the outside is touched by 6 other discs. On the spherical surface, the construction appears to succeed at first. The smaller the radius of the disc relative to that of the sphere, the more promising it appears in the beginning. As this construction process further progresses, however, it becomes more and more clear that the arrangement of the discs in this manner without overlaps is not possible, as it should be possible according to the Euclidean geometry of the plane. In this way, even the creatures who cannot leave the spherical surface, and who are also unable to look out of the sphere into three-dimensional space, could still determine, simply by experimenting with circular discs, that their two-dimensional space is not Euclidean but rather spherical. Spherical universe? According to the latest results of the theory of relativity, it is probable that our three-dimensional space is also approximately spherical. That is to say, the laws of relative positioning of rigid bodies in space are not given by Euclidean geometry, but rather by spherical geometry, if only approximately, as long as sufficiently large parts of space are subjected to consideration. Now, this is the place where the reader's imagination meets resistance. No one can imagine this thing, he declares indignantly. You can say that, but you can't imagine that. I can easily think of a two-dimensional spherical surface, but not its three-dimensional analog. Spherical geometry on the plane. This mental barrier should be overcome. The patient reader we'll see that it is by no means a particularly difficult task. To this end, we will first return to the consideration of the two-dimensional geometry of spherical surface. In the figure shown below, let K be the spherical surface, E be a plane tangentially touching it at S. This plane is indicated in the drawing as a bounded surface to make it easier to imagine. Furthermore, let L be a small disk on the surface of the sphere. Let us now imagine a point light source placed on N of the spherical surface that is the diametrically opposite point of S. This light casts a shadow L' from the disk L on the plane E. Figure. Projection to a plane. For every point on the sphere, in fact, there is associated a shadow of the same point on the plane. If the disk L moves on the sphere K, its shadow image L' also moves on the plane E. If the disk L happens to be at S, then it coincides almost exactly with its shadow at S. If it moves upwards on the spherical surface from S, the disk shadow L' on the plane E also moves away from S on the plane outwards, and it becomes larger and larger. As the disk L approaches the point of the light source N, and as L eventually coincides with N, the shadow ultimately moves off to infinity, and its size becomes infinitely large. Now we ask the following question. What are the laws of relative positioning of the shadows of disks L' on the plane E? Well, if you think about it, it is evident that they should be exactly the same as the relative positioning laws of the disks L on the spherical surface. For every original figure on K, there exists a corresponding shadow figure on E. If two disks touch each other on K, their shadows also touch each other on E. The disk shadow geometry on the plane corresponds to the disk geometry on the sphere. If we regard the disk shadows as rigid shapes, then the spherical geometry of K that is applicable in relation to the circular disks now applies on plane E in relation to these disk shadows. In particular, the plane is finite with respect to the rigid disk shadows, since only a finite number of the disk shadows can fit on the plane. At this point, somebody will say, "That is nonsense. The disk shadows are not rigid shapes. We only need to use a small measuring stick on the plane E to convince ourselves that the shadows become larger and larger in size as they move from S on the plane towards infinity." But what if the measuring stick on plane E behaved in the same way as the disk shadows L'? Then it would no longer be possible to state that the shadows grow as they gradually move away from S. This statement would no longer make any sense at all. In general, the only thing that can be said objectively about these disk shadows is that they behave geometrically in exactly the same way as the rigid disks on the spherical surface in the sense of Euclidean geometry. It is worth noting that our statement in itself, about the disk shadows growing in size as their distances increases from S to infinity, has no objective meaning, as long as we do not have any Euclidean rigid bodies pointing to E which can be moved and which can be used for comparison with the disk shadows on E. Moreover, with regard to the laws of relative positioning of the disk shadows L', the point S is no more preferred on the plane than on the spherical surface. The illustration of the spherical geometry on the plane given above is useful to us because this idea can be easily transferred to the three-dimensional case. Spherical geometry of 3D space. Let us now imagine a point S in our three-dimensional space, and a large number of small spheres L', all of which are identical in that any two of them can be brought to coincide with one another in space. These spheres, however, are not rigid in the sense of Euclidean geometry, but their radii increase again as judged in the sense of Euclidean geometry, when they are moved from S towards infinity. We further assume that this increase in their radii takes place following exactly the same law as that of the radius increases of the disk shadows L' on the plane. Now that we have understood the geometrical behavior of our L' spheres in our mental picture, let us suppose that in our space there are no rigid bodies at all in the sense of Euclidean geometry, but there are only bodies having the behavior of our L' spheres. Then we have a clear picture of three-dimensional spherical space, or more precisely, three-dimensional spherical geometry. Our small spheres must now be considered rigid spheres in this geometry. Their increase in size with distance from S in our space is not noticeable when measuring with measuring sticks, any more than in the case of the disk shadows on the plane E. This is again because the measuring stick itself behaves exactly in the same way as the spheres. Our space is homogeneous. That is to say, the same spherical configurations are possible in the neighborhood of every point in space. Our space is finite, because as a consequence of the growing of the spheres, there is only room for a finite number of them in our space. We have thus gained a clear mental picture of spherical geometry by relying on the exercises of thought and imagination in the area of Euclidean geometry as a learning aid, which we are more familiar with. There would be no difficulty in going deeper and making the ideas thus gained more realistic by carrying out further imaginary constructions in our mind. Nor would there be any difficulty in getting a realistic mental picture in the case of the so-called hyperbolic geometry in an analogous way. I only wanted to show here that we need not cave in to non-Euclidean geometry. The human faculty of imagination is by no means constrained in the face of non-Euclidean geometry. Albert Einstein, January 1921. Afterword by the translator Harry Yoon, Ph.D. Mathematics is not physics. This may sound obvious to some people, but it is a rather minority opinion. In fact, modern theoretical physics is pretty much a branch of mathematics. Einstein expresses more or less the opposite view in this article. That is, mathematics and science are entirely separate. But with some constraints, a certain geometrical framework can be viewed as a branch of physics, which he calls practical geometry. Ever since mathematics was invented, or discovered depending on your philosophy, the vast majority of people believed that mathematics represented reality. Pythagoras and his pupils philosophized that everything was a number, in particular, integers and rational numbers, i.e., the ratios of two integers. When they ran into irrational numbers, they couldn't make sense of them, because they believed that irrational numbers couldn't correspond to nature. They tried to keep it a secret. According to a story, one person who attempted to divulge the secret was taken out to the sea on a boat. Nobody knows what happened to this person. Apparently, he didn't come back. In the dawn of modern physics, in the 16th-17th centuries, people started realizing the power of mathematics in describing physical phenomena. For example, Kepler successfully applied Greek mathematics, such as conic sections, e.g. ellipses, in explaining the planetary motions. He was initially tried to use Plato's perfect solids, but it didn't work out. He probably knew even then that you could not just blindly apply mathematics. Galileo was the first person on record who explicitly stated that mathematics was the language of physics. He didn't suffer fools well, and he was somewhat too direct in expressing his opinions towards his rivals and authorities. We all know now what happened to him. He offended too many powerful fools, and he ended up spending the last 9 years of his life in home arrest. It was right after the publication of his book, Dialogue Concerning the Two Chief World Systems, 1632, which advocated the then radical heliocentric view of the world. Modern mathematics really began at the time of Descartes, Newton, and Leibniz. Their inventions, namely calculus and analytic geometry, are ultimately at the foundations of virtually all modern branches of mathematics. The next revolution in mathematics, as far as relativity is concerned, was the invention of hyperbolic geometry by Gauss, Bolyai, and Lobachevsky, and that of differential geometry by Gauss and Riemann in the first half of the 19th century. Another innovation in geometry came from Einstein's former mathematics teacher, Hermann Minkowski, and hence somewhat indirectly from Einstein himself. Before Minkowski and possibly Poincare, nobody considered the non-positive definite metric. That is to say, the distance had to be either zero or positive. Anything else was probably unthinkable. Minkowski, when he learned about the special theory of relativity created by one of his former students, immediately saw how it could be fit into a geometrical structure, although he initially had to jump over the mental barrier that distance is always positive definite. This is now called pseudo-Euclidean geometry in general, beyond the specific geometry used for special relativity, namely the four-dimensional Minkowski space. Einstein talks about this kind of mental barriers in the article. Although it is a small contribution in hindsight, nobody ever thought of this possibility of negative distance before Minkowski and Einstein. What does a negative distance even mean? For over 2,000 years, geometry meant Euclidean geometry, that is, the geometry of a flat space, specifically in the 2 and 3 dimensions, with a positive definite metric according to the Pythagoras theorem. Interestingly, despite the fact that the Earth was roughly spherical when viewed as a two-dimensional surface, nobody really considered spherical geometry, or elliptical geometry, until the turn of the 20th century. As far as geometry was concerned, the Earth was flat, and Euclid ruled the world. It is hard to speculate why that was the case at this point, but one obvious reason would have been the fact that Euclid's fifth axiom, the parallel axiom, did not hold on a spherical surface, nor on a hyperbolic surface. Another reason would have been the fact that a sphere has a finite size, whereas Euclid's plane is infinite, as Einstein goes over in this article. At the end of the lecture, Einstein provides an interesting way to visualize or get a mental picture of both two-dimensional and three-dimensional spherical spaces. We may call them the Einstein plane and Einstein sphere, respectively. There are constructions, for example, to map an infinite hyperbolic space into a finite plane, e.g., the Poincare disk. The Einstein plane maps the finite 2D spherical space into an infinite plane in the Euclidean sense. But the Einstein plane is indeed finite as explained in the lecture. The same can be said with respect to the Einstein sphere. Now, the ultimate question, or one of the ultimate questions in modern cosmology, is whether our universe is approximately spherical. Einstein, as of over 100 years ago, clearly believed that that was the case. The current astronomical observational data, however, suggests that the universe is flat, or very close to flat. Is there a reason why the universe has to be flat? Or is it just a coincidence? The Einstein's Books Project. We are working on new translations of some of the more important writings of Einstein into English, e.g., using more modern terminologies. Your purchase of this book supports our effort. Learn relativity from Einstein's book, Einstein's Relativity, the Special Theory and the General Theory. This book is not available on Amazon.